May, June 2019, paper 6, variant 2. Question 1. A student is investigating moments using a balancing method. You have an apparatus. A student places the meter ruler without the loads on the pivot, and she adjusts the position so that the meter ruler is as possible to being balanced. Okay. She keeps the ruler at this position on the pivot throughout the experiment. Explain briefly why this position on the pivot may not exactly be the 50 centimeter mark. Why may this position of balancing may not exactly be the 50 centimeter mark? Yes, because the center of mass may not be exactly at the 50 centimeter mark. Okay, so the center of mass may not be exactly at the 50 centimeter mark. Okay. She places a load P on the meter ruler so that the edge of the furthest is exactly at 10 centimeters at this 10 centimeter mark. So P, okay, the edge is at 10 centimeters, and then she measures the distance B between the center of the load. She repeats the procedure, okay, with the edge of P at 15, 20, 25, 30 marks. Okay, no problem. Can I plot the graph of A and B? Okay, so A is on the y-axis. First of all, you have to write down A slash centimeters on the y-axis, B slash centimeters on the x-axis. So B slash centimeters on the x-axis. And then start both axes from the origin. So I have to, even though it might not be the best thing to do, but you have to start from 0 and 0. Both axes will start from 0. Now, can I plot A? Yes, A is 18 all the way up to 38. So I think we need to, yes, 10, 20, 30, and 40. This would be the best way to plot A and B as well. Okay, so 10, 20, 30, 40, and 50. Let's plot the points. Let's zoom in a bit. So, first point, I'll start from 22 and 18. 22 and 18, this would be easy. We have the point. Here is 22 and here is 18. This is the point. Okay, 22 and 18. The second point, okay, the second point is 27.2, which is 27. Easy. 27 and 23. We have 27, okay, and 23. Where is 27? This is 27 and 23, so it's right over here. This is 27 and 23. Next point, 33.6 and 28. So it's 33.5. You can write it down as 33.5 or 34. Okay? 33.5 and 26. Where's 33.5? 26. So this is 26 and 33.5. So here is the point. This is the point. 26, wasn't it? 28, I'm sorry. It's 28. It's at this point. Okay, let's remove this one. And then the next point is 38.5, 33, 38.5 and 33. Need to be very careful. 38.5 and 33. So this is the point right over here. And then the last point is 44.5 and 38, 44.5 and 38, which is right over here. Now, let's draw a straight line. Yes, this is best fit line. It will be a straight line. It will not be a curve. And then can I find G? And I think I need to extend the graph until it reaches, okay, until it reaches the x-axis. Determine the intercept C on the x-axis of this graph. Okay, so let's first of all draw the line. Draw the straight line. Using the ruler, you draw a line passing through most of the points. Okay. Let's reach 12. Yeah. Okay. So this is a good representation of the graph. You might have 1 or 2 points above, 1 or 2 points below, which is okay, which is a good representation or a good drawing for this graph. Anyway, can I find the g? Can I find the gradient? Yes, the gradient would be y2 minus y1 over x2 minus x1. We need to take two very far away points. Let's take this point. With this point, you have to draw it on the graph. You have to draw it on the graph. The uh, y-axis and the x. You have to draw the rise and the run. Okay, and then y2 would be 38 minus. Okay, you can take the numbers from the graph if you want to, from the table if you want to. So 38 minus 18 over 44.5 minus 22. 38 minus 18 over 44.5 minus 22. This would give you a final answer of around 0.91. Around 0.91. Okay, 0.91. Now, can I find the c-intercept or whatever, the intercept on the x-axis? Can I find the intercept on the x-axis? Yes, we can find the intercept on the x-axis. The intercept here would be around 2. So it has reached this point at 2. So this is the c-intercept, right? This is the c-intercept. Let me remove this line. Okay, so the c-intercept would be 2. Now, on figure 1.1, measure the width W of this load. Can I measure the width W? Yes, I can measure the width. The width would be using the ruler. Okay, using the ruler, it would be around what? Yes, around 2.5. Around 2.5. So the width is around 2.5 centimeters. Another student suggests that the value of the c-intercept should be equal to half the width. Should be equal to what? Half the width W of the load P. State whether the results suggest or support this suggestion or not. Half the width. So basically, you need to divide 2.5 divided by 2. 2.5 divided by 2. Can I say do 2.5 divided by 2? Yes, 2.5 divided by 2 is 2.5 divided by 2 is what? 1.25. So is C equal to 1.25? C is 2 and half the width is 1.25. So they are not equal and they will not be within the limits of experimental accuracy. So for example, if I divide 2 divided by 1.25, definitely the difference would be much greater than 10 or 15%. So the statement now we need to say that no, they are not equal. Okay, no, not equal. Why aren't they equal? Okay, because the numbers or the values are far apart. The values are far apart. They are not within the limits of experimental accuracy, or you can say exceeding the limits of experimental accuracy. Okay, not bad. So just one practical reason why is it difficult to obtain accurate values for A or B. Now you have A or B, you need to measure the distances, these distances, A and B. Why? What is one practical difficulty? One practical difficulty, a very famous difficulty, is that it is already quite difficult to obtain the balance. It's already quite difficult to balance this ruler. You have the ruler above the pivot, so it's already very difficult to obtain this balance. It's difficult, okay, to obtain a balance. You cannot keep the ruler balanced for that long. Now, moving on to question 2. The student is investigating the rate of cooling under different conditions. You have the thermometer in beaker A with a lid, and then you have the thermometer in beaker B with a mat below the beaker. So these are the two different conditions. That beaker A has a lid, and beaker B doesn't have a lid, but it has a mat below it. Thermometer in figure 3.1 shows the room temperature theta R. What is theta R? Can I find theta R? Yes, from this reading, the theta R would be around 22 degrees. Okay, it's around 22 degrees Celsius. Okay, now she pours 200 centimeters cubed of hot water in A and then in B. And then she starts the stopwatch, or he starts the stopwatch every 30 seconds. Can I complete the column headings? Yes, I can complete the column headings. First of all, the time is in seconds, the temperature is in theta, is in degrees Celsius, and seconds and degrees Celsius. Look carefully at the readings. Tick the box to show your conclusion from the readings. Can I tick the box to show the conclusion? Okay, 81 to 76. What is the difference between 81 and 76? The difference is only 5 degrees Celsius. From 83 to 77, the difference is 6 degrees Celsius. Is there actually a difference? There is no significant difference, no? There is no significant difference. Justified conclusion. How can I justify the conclusion? By writing down the values. So in beaker A, the difference was only 5 degrees Celsius. In beaker B, the difference was 6 degrees Celsius. So they are quite close. In beaker A, the temperature loss, okay, the temperature loss was only 5 degrees Celsius. And in B, the temperature loss was 6 degrees Celsius. That's it. Okay, that's very close. You can say that they are very close. Very close. Okay, now let's move on. Question C. A student plans to repeat the experiment using the same apparatus and the same volume of water. Suggest one change to the procedure that will decrease, again, think about it, decrease the rate of cooling of the water. How can I decrease the rate of cooling of the water? If you want to decrease the rate of cooling of the water, what should you do to the experiment? I want to repeat the experiment, but I want to decrease the rate of cooling. What should I do to the experiment? Yes, I should reduce the initial temperature. Yes. Okay, decrease the initial temperature. Decrease the initial temperature. Okay. Nice. State one precaution that you must take in order to record accurate temperature readings. One very important precaution. What is one very important precaution? Take the readings perpendicularly to avoid, okay, take the readings perpendicularly to avoid parallax error. Okay. To avoid parallax error. Okay. Now, suggest two variables that must be controlled in order to make this experiment a fair test. Okay, to make this experiment a fair test. What are two variables that have to be controlled? Yes, the volume of the water, the room temperature, the same initial temperature. Okay. Hmm. Okay, same initial temperature. I think the volume of the water in this case might not be correct. Why? Because he already has the same volume of the water. So same initial temperature and same room temperature. Same room temperature. Okay? It is important to view a measuring cylinder correctly to obtain an accurate value. Okay, tick the box that gives the best description of how to read a measuring cylinder. Definitely, you have to take the reading from the measuring cylinder at right angles, which is perpendicular. I'll say take the reading perpendicularly to avoid the parallax error. Yes, that is correct. A student, question 3. Student investigates the electrical resistance. She uses the circuit shown. You have P, L, a meter, a voltmeter. Write down the readings of V1 and I1. What is the voltage? Voltage is 3 point what? Yes, 3.6. What about the current? 0.3. So 3.6, 3.6 volts and 0.3 amperes. That's easy. Calculate the resistance. Can I find the resistance? R equals V1 over I1. So R equals 3.6 over 0.3, which is 12. Yes, 12 ohms. She connects the voltmeter across the lamp. She records the potential difference. Okay, 2.4 volts. Can I find R2? Yes, I can find R2. So 2.4 divided by 0.3. What is 2.4 divided by 0.3? It is 8 ohms. Now she replaces the resistor P with another resistor Q. She records V3 and I2. So V3, 3.5, I2, 0.31. Can I find R3? Yes, 3.5 divided by 0.31. It is 11.3 ohms. 11.3 ohms. Okay, so far so good. State whether the results R1 and R3 suggest that the resistor P and Q have the same value within the limits of experimental accuracy or not. So what was R2? R2 was R1 was 12, the resistor P, and R2 is 11.3. Are they equal or not? Yes, they are equal. How can I find them? How can I find if they are within the limits of experimental accuracy? So 12 divided by 11.3. What is 12 divided by 11.3? This would give you 1.06. 1.06. So 0.06 is 6%, which is definitely within. This is 6%. So it's definitely within the limits of experimental accuracy. So the statement, yes, they are similar. Yes, they, okay, are the same. Yeah. And the justification, you have to say that the values are close. Values are close and within the limits of experimental accuracy. Values are close and within the limits of experimental accuracy. The limits can be up to 10%. Okay, up to 10%. In some rare cases, okay, some rare cases, we can push the limits up to 15%. Not rare, but some. So, for example, if the percentage is around 12% or 13%, sometimes we can consider it to be yes. So, yeah, okay, 13% might be acceptable. 13% might be acceptable. But for example, if the difference is 30%, definitely not acceptable. Definitely not acceptable. Now, she records V3, V4. and R4, she suggests that the change in the resistance for the lamp from part C is due to the change in temperature. Okay? Due to the change in temperature. Is that right or wrong? Suggests an observation she could make to confirm that the temperature of the lamp changes. So what could she do? Yes, it has to do with the brightness. It has to do with the brightness. Why does it have to do with the brightness? Because if the temperature changes, then the resistance will change, and therefore the voltage will change, and the brightness will change. Okay, so the temperature might affect the brightness of the lamp. Brightness changes. Hmm. The brightness of the lamp changes. Okay? Hmm. That's it. I know this might be a new question. Brightness of the lamp changes. What does this have to do with the voltage? But yeah, we might have some of these questions. Complete the circuit diagram to show that two resistors and the lamp are connected in parallel. The voltmeter is connected to measure the potential difference across the resistors and the lamp. So you need to draw what? You need to draw two resistors, a lamp, and the voltmeter all in parallel. Two resistors. Okay. You have two resistors, a lamp, and a voltmeter. They are all in parallel. Okay. State the name of the circuit component that you would add to the circuit you have drawn to control the current. Which circuit component controls the current? Hmm. Yes, it is a variable resistor. A variable resistor. Do I have to draw with the ruler? No, you do not have to draw with the ruler. But you need to draw it neatly. Okay, question 4. Student is investigating the relationship between the thickness of a converging lens and its focal length. The thickness and its focal length. The focal length is the distance, okay? And you can find the equation, you can use this equation to find the focal length, uv over u plus v. What is u and what is v? U is the distance between the object and the lens. V is the distance between the lens and the image on a screen. So you can measure U, then you can measure V, and then you can find F. So what is he doing? He's changing the thickness of the lens and finding the focal length. This is the whole question. Plan an experiment to investigate the relationship between the thickness and the focal length. Thickness and focal length. Okay, that's it. That's the whole question. That is the whole question. Let's go. In your plan, you should draw a diagram to show the arrangement of the apparatus, labeling U and V. So on this diagram, we need to draw the object and the screen. So this is the object. Usually the object is on the left. So you have an illuminated object, for example, a candle or something. And this is the object. And the distance between the object and the center of the lens is called U. And then you have the screen. Okay, this is the screen. And the distance between the lens and the screen is called, okay, this is called V. So this is the diagram that we need to draw. Explain briefly how you would carry out the experiment. Okay, how you determine the thickness. This is quite an important point. How can you determine the thickness of each lens? So how can you determine the thickness, and then we need to draw a then we need to draw the table. Okay, the thickness, when you think about it, this is a very small lens. Okay, you won't be able to use the ruler directly. You won't be able to use the ruler directly. So what should you do? You should put the You should put the lens between two blocks. You have to, yes, use two wooden blocks. Put the lens between these two wooden blocks and measure the distance. Okay. Now we need to write it down. First of all, what is the variable that we're changing? What is the variable that you are changing? The range of values. The range of values. The thickness of the lens, for example, we're not talking about the thickness of the lens. We need to state five different values, five different logical values for the thickness of the lens. What are five different logical values for the thickness of this small lens? We could say 1 centimeter, 2 centimeters, 3 centimeters, 4 and 5 centimeters. Definitely small lenses. So these are the values. The question didn't actually ask me to find any constants or write down any missing apparatuses. He didn't. He didn't need that. Why? Because we have the apparatuses. We don't need to write down any precautions. We need to write down the steps. The steps. How can I carry out this equation? The steps. How can you carry out this experiment? Think about it carefully. If you want to carry out this experiment, first of all, you need to find the thickness of each lens. How can I find the thickness of each lens? By using, by putting it or by placing it between two wooden blocks. So place each lens between two wooden blocks and measure the distance between them. Distance between them to find the thickness of each lens. To find the thickness of each lens. We placed them between two blocks. We found the distance. And then what should we do? Okay, we should measure the distance u and measure the distance v. Okay, we have the setup now, and then measure the distance u and v. Distance u and v. We know u is the distance between the object and the lens, and v is the distance between the lens and the screen. But we have to say that we need to move the screen slowly. Okay? Move the screen or the lens or the object slowly until you have a clear image. Move the screen slowly until a clear image appears on the screen. Or you can actually say this step before measuring U and V. Again, it is okay. We can move the screen slowly until a clear image appears on the screen, and then measure U and V, which is okay. Then, what should I do? I wrote down the steps. I can calculate F now using the equation F equals, okay, calculate F, okay, using the equation F equals UV over U plus V. Oh, that's easy. Please. Then, can I draw a table? Yes, I can draw the table. The table has only two columns. It has only two columns. The thickness in centimeters or in millimeters if you wanted the thickness to be 10 millimeters, 20, 30, 40 millimeters. Again, it's okay. And the focal length in centimeters. You have the table. We wrote down the steps. Okay. And then we can write down a quick conclusion. I know he didn't want a conclusion. Okay. Okay, he did not want a conclusion, but we can write down a very quick conclusion in which, conclusion, for each lens, repeat the experiment, repeat the experiment, and take average. Okay, and take average. When you repeat the experiment, take average. Then what should you do? Record the readings in the table. Record the readings in the table. Then, when you record the readings in the table, what should you do? Compare the results. Compare the results using a graph, for example. You can plot a graph with the thickness and the focal length. Okay? Okay.